Um, okay, so I'm gonna go ahead and share my screen. Huh. So we've got TAs, we've got this PowerPoint that we usually go through, and this is kind of like a bird's eye view of some introductory stuff. So we're gonna move through this kind of quickly, and then I'm gonna talk about some tricky stuff in C++ that I know people have struggled with, and I'm actually gonna walk through some examples. Oh, and please stop me at any time if I go over something that's confusing that I don't explain well enough. Just feel free to unmute yourself. Okay, so let's see the topics for today. This is week 1 and week 2 slides. So we're going to be covering pointers, stack versus heap, vectors and array, templates, and we're not going to talk about big O. That's going to be next week. So pointers and arithmetic syntax. So I'm sure y'all are familiar with pointers. It's one of the building blocks of C++. It's what makes it, I think, in my opinion, a more useful language than some other languages that don't allow you to interface with memory directly. Um, Professor Lake really, really, really loves to give quizzes about very specific pointer syntax, right? So there's going to be a lot of quizzes, and huge hint, this is going to be on the first exam pretty heavily, is you see an expression like this, right? So imagine P is some pointer, right? P is this green arrow to the first element of this array. And then you see an expression like, parentheses, dereference P, postfix increment. Like, how do you evaluate that? What actually happens? So we're going to go through some examples. Uh, I think also worth note, and just memorize this, please. Just know this for the rest of your life, that the plus plus operator has got a higher precedence than the dereference operator. So if you see something that would be potentially an ambiguous expression like this, right? Like you've got the dereference on one side and the postfix increment on the other side, the postfix increment will always happen first. So just know that is your order of operations, more or less. So here's the first example. So we've got the one that I was talking about, potentially could be ambiguous depending on how the language interprets this. So because I said that the plus plus takes precedence over the dereference, essentially this expression is equivalent to this, right? So it's like we do the increment within these parentheses, and then we dereference whatever the incremented pointer is going to be. This happens to be a postfix increment, which means that the increment happens after the expression has been evaluated. So P++ will return you an arrow to the first element in the array. And then as soon as the expression has been evaluated, which is this line, the pointer will then be incremented to the next spot. So a very common quiz or test question that you're going to see a lot is maybe you see this expression right here, like star p plus plus, what is the value of p after this line executes? And in this case, we increment the pointer after we evaluate the expression, and we print the value that it points to on this line. So, all this kind of thing would be fair game. Okay, now if we explicitly say that we are going to dereference the pointer before we do the plus plus increment, the parentheses make the order of operations thing irrelevant, right? So whatever happens in the parentheses is what happens first. So if we do star p plus plus, now we're saying dereference this pointer, and then this location in memory is going to get incremented with postfix. So what happens here is when we evaluate this expression, star p is going to dereference this pointer, which will give us 7. The postfix will be applied after this expression is evaluated, and then on the next line, p will point to a value of 8. And let's see. Oh, someone asks, will we have access to these slides after the review? Yes, yes. Remind me, and I will post this link in the chat. Okay, so again, same issue here. So if we have parentheses, that takes precedence. So we're going to dereference p, but we're going to do a prefix increment. So it's going to happen in the expression that it's called. Okay, so also I would recommend, for your own sake, for your sanity, just go like open up C++ on your computer somewhere and just type 20 of these examples and keep doing it until you're very confident about it, because I promise you this will be on the test, the first one at least. Okay, stack versus heap. So far, we're just reviewing concepts I think you would have seen in 121, but briefly, stack is temporary memory because it's allocated contiguously. So when the compiler compiles your code, it needs to know exactly how much space to put into each scope because the stack is, fixed per se. And if you need to access more space than that, you're going to have to start using the heap, which is a separate area in memory. Examples of stack versus heap. So if you declare a function, like in this example, you've got int, this function, it takes some kind of inputs and returns a simple output. The compiler can allocate just enough space for that to happen. And when you compile your program and it runs, the stack will have been given enough space to make sure that this is good. But imagine you have a program that doesn't know how much space it needs to have, or maybe you have an array of variable size. Well, in that instance, you can declare a pointer to the heap, which is a separate area of memory, and then allocate dynamic memory there. Um, I think the theme of today's Sunday review is just going to be going over all of the like tricky things that, maybe people are a little bit unsure of. Uh, and so the first thing I wanted you to remember was the fact that the plus plus operator takes precedence over dereference. That's something to just memorize forever. And then here's another thing to memorize forever when you're working with the heap and dynamic memory, you can one-to-one line up your new and your delete keywords. So that's just like that's a little trick of the trade that I think you should just memorize and keep with you for forever. So when you are storing things on the heap, typically that syntax is going to look like what you have right here on the right. So int star pointer is equal to new, and then some array or some object that you put on the heap. And every time you call the new keyword, somewhere else in your code, you're going to have to call the delete keyword, right? So these two are like a pair, they match up. Similarly, here we have int star allocate number is equal to new, and then we're putting an integer on the heap. And same thing, we're deleting um, the memory that's stored at this pointer. And so a really helpful trick that somebody told me one time that is just stuck with me forever that I think is super helpful is that not only do the new and the delete keyword line up, but the syntax used with them lines up as well, right? So there's been a lot of confusion in the past about like when do I use the delete with brackets and when do I use the delete without brackets? Well, as a rule of thumb, if your new keyword uses square brackets, right? So here we have new int and then square brackets 5. Your delete keyword needs to have square brackets also. And then likewise, if your new keyword does not have square brackets, you don't need square brackets in your delete statement. So hopefully that saves you some headache. And then common misconception is that alloc num would be an int pointer variable. But the variable itself is stored on the stack. So this is like a common like maybe I didn't word that right. So while this pointer is in fact pointing to an address on the heap, the pointer itself, the address that it's pointing to, is stored on the stack. So alloc num is a value on the stack that points to the heap. And this is like a very common like haha gotcha quiz slash test question that you're gonna see. It's like, where is alloc num stored? Well, this pointer is stored on the stack, and if they asked you where is like the address that it points to, where is that? That's on the heap. So very common trick question type. Um, okay, let's see. Next we've got arrays and vectors. So I'm not going to be talking about this too much. I recorded a video for the first assignment that I'll release it on YouTube. Kind of walks you through the starter code and what to do. So if you have questions about PA1, probably they'll be answered there. So I'm gonna go over this briefly. Essentially, an array is a primitive data type. It's like a contiguous memory, and a vector is a bunch of logic that manipulates that array that's kind of wrapped into a nice package. If you want to look at the C++ documentation, it's very well written. Okay, templates. We're going to be talking about this more later. So when you have a function, like for instance, here we have a function t, my max, and then it takes two parameters, x and y. just like you can pass an argument to a function as like a parameter, right? So we have x and we have y. You can also pass a data type as a parameter, and that's done with templating, right? So imagine we want to have this mymax function compare integers. Well, then we can pass in t as the template, being an integer, and then suddenly our function works with integers. It would be the same if we wanted to compare strings or if we wanted to compare objects or what have you. And this is useful because it's going to come up, I think in PA2 is the one where it starts to be like really, really important, where you're going to have a function that you need, um, like you need to compare different data types with the same logic, with the same function. So rather than copying and pasting your integer code for double type or char type, it would be better to just pass in the data type as its own parameter. So when you see something like this, template, pointy brackets, type name t, just think that t is like another parameter to this function. And then after the templated argument, anytime that t appears will be the parameter that you passed in. So on the left here, we've got the return type. So that means that the function will return whatever your templated parameter is. You have tx, which means the inputs are the templated type. And then when you actually call the function, you have to specify the template in pointy brackets and then the parameters in regular parentheses. Uh, let's see, we've got some examples there. Maybe check those out after I've shared these slides. And then, okay, so iterators, again, gonna talk about this in the video about PA1. Um, I guess it's worth mentioning that iterators are a very common point of confusion, but an iterator is to a pointer what a vector is to an array. That's kind of an analogy that I think probably would clear up some confusion. So, right, like your array is a primitive data type. And if you want to expand that array, right, if you want to like double the size and copy all of the old contents over, or if you want to insert something in the middle, that takes a bunch of complicated logic that you would rather not have to rewrite every single time. So it makes sense that we would have a vector class to wrap all of that logic into one nice compact package. That way we can work with arrays without having to write a bunch of code for it. An iterator is the same idea. So whereas the vector houses an array and all of the logic needed to maintain that array, an iterator contains a pointer and all of the logic necessary to maintain that pointer. And so I do apologize that it's going to be difficult to understand why iterators are useful on the first assignment, but by the time you get to a linked list or a graph, it's going to start making more sense. Okay, another thing you might have seen that is new in 221 since 121 is copy and move semantics. So I believe in 121, someone correct me if I'm wrong, I believe
But the next 3 days it's raining like really bad.
uh,
Thunderstorm.
can you repeat that? I'm sorry. Uh, okay. Someone made a comment. My hearing is not the greatest. Uh, let's see. So yeah, so I believe you've seen copy being like copy assignments and copy constructors. We're gonna add in a new paradigm, which is the move paradigm. And I don't think the animations are working for some reason. Maybe I have to be full screen. Uh, but we're gonna talk more about this later when I actually show examples. Um, Essentially, what you need to know is that if you learned about shallow copying in 121, move is like kind of an intentional shallow copy. So in this example, we have a green pointer and a red pointer. If we want to copy the array that the green pointer points to, then we give an exact copy to a different pointer and a different space in memory, right? So we have this address in memory that contains, this amount of data, and then we have a different spot in memory that contains identical data. Whereas for moving, we could just change which pointer has access to the same spot in memory, which is like this. So we're just flipping between the green and the red pointer. Um, Probably skip this stuff, talk about this later. Okay, and that's it for the slides. We'll talk about Big O next week, I believe. Does anyone have any questions so far? Let's see, let me check the chat. Let's see. Someone asks, could you explain what a move semantic is? I'm unsure of what a semantic is overall. Okay, good question. Let me go ahead and pull up, I'm going to pull up a code example, and maybe this will make it better. So, would someone confirm that you can see VS Code? Uh, Someone unmute, maybe help out.
We can see it.
Okay, appreciate it. Thank you. All right, so to understand move semantics, you first need to understand references. So I'm going to talk through this slowly. So if you're a C++ wizard, please just, bear with me. This is not a concept that I feel it was explained to me very well when I took 221 personally. I had to do most of this like learning actually on my own. So I completely understand how tricky this concept is. So in this code example that I've got right here, you can see I've basically just got like include IOStream, namespace std, nothing too scary. I define a class. So within the dog class, we've got a private member, which is an integer, and then we've got three constructors. Okay, so the first constructor is the default constructor. So if we construct a dog class with no parameters, we just set our private member to 0. If we've got a constructor with copy semantics, so if we construct a dog and we pass to the constructor an int, so an actual copy of a reference to an actual int that has been assigned in memory, then it's going to print out and tell us that we called the copy constructor. If we pass move semantics to a constructor, as opposed to copy semantics, then we're going to print out you called move and we're going to move the value. So I haven't quite explained what is copy semantics and what is move semantics, but if you take my word for it that these two constructors right here, this one is the copy and this one is the move semantics, then let's look at the differences between these two, and maybe that'll start giving us a clue as to what's going on. So for the parameters of these two constructors, that's like the most obvious difference, right? So the parameter for this constructor is a constant integer reference, right? To some integer, right? And this one is an integer R value reference with 2 ampersands at the end. So here we've got the const keyword, the data type, and then an ampersand after the data type. And what that's saying is const means you can't modify this parameter. So when the constructor gets called, you cannot modify the value that gets passed in. The value that gets passed in will be an integer, and not only will it be an integer, but this ampersand means that it's a reference. So for instance, in our code, we declare this integer right here to be 42. So mouse is 42. This is a variable. This is a place in memory, right? And so if we construct our object like this, right? So dog is equal to, it gets constructed around mouse, then that is going to call this constructor, which takes in mouse. So mouse will be this parameter as a constant, so it can't get modified, but also it is a reference. So it's actually pointing to the space in memory where mouse is stored. Now, that's an L value. Because if an integer, in this case 42, is assigned to something on the left hand of an assignment expression, the thing on the left hand is referred to as an L value, okay? So this assignment right here, as you can see, int mouse is something that is referenceable. It is on the left hand of the expression, therefore is an L value. Something that appears on the right hand of an expression exclusively, like the 42, is an R value. So when you see an assignment like this, you can break this. While it is true that both of these are integer types, right? So 42 is an integer and mouse is an integer. You can break these reference types into two categories. You've got L values and R values. L values exist somewhere in memory, so they have a valid address and they contain the data, whereas R values exist solely for the purpose of assignment and go out of scope immediately after the expression executes, right? So if we call this first constructor dog, dog1, 42, we're passing in 42, which is an integer. But which of these constructors do you think it calls? It doesn't call the L value constructor, it calls the R value constructor, right? So the ampersand refers to R value. So it's asking for a value that would appear on the right hand of an expression that doesn't exist somewhere in memory, right? So 42 is not somewhere in memory. I could change this to any integer, right? That it could be 400, it could be 1,000. You know, on your hard drive, in your memory, you don't have a place that your computer goes to when it wants to find 42. It's something that is calculated purely for the sake of being assigned somewhere else. And as soon as line 40 in this code executes, 42 is gone. It exists purely to be assigned. Therefore, it is an R value. And to catch an R value in a constructor or to pass an R value to an argument, you've got to use this semantic, which is the data type ampersand, which is different than the reference to an L value. So let's go ahead and compile this code and see what happens. So if my assessments and what I just said is correct, then we're assigning int mouse, which is going to be an L value, to 42, which is an R value. So mouse will store 42. When we construct the first constructor around an R value, it should call this code right here and print uCalledMove. This next line, constructing an object around an existing L value, will alternatively call this constructor right here. And then just as an extra little tidbit, if we call std move on an L value, it will pass the L value as an R value, and it will hit the second constructor again. So if what I've said is correct, what we're going to see is uCalledMove, uCalledCopy, uCalledMove. So I'm going to go ahead and compile this code and see, it was 16, and then our 60. Okay, and then as you can see, it generates executable. Okay, so in fact, it is as I suspected. You called move, uCalledCopy, uCalledMove. So maybe just another second to talk about what happened here. So why is it that passing 42, which is obviously an R value, right? Obviously something that exists only to be assigned. 42 is not stored somewhere in memory. Why does that go to the same place that calling std move on an L value will take you to? Well, when you call std move, essentially you are saying that this parameter has got access to the place in memory that used to have access to this value, which is very similar to the example that we had on the slides of two pointers and you're just switching which pointer has access. So now the namespace mouse will not have access to 42 guaranteed because that access is being passed to this function so that it can be assigned the way that an immediately out of scope R value would be assigned. And this is technically more efficient if we don't care about what happens to mouse in our namespace. Okay. So does that help at all? See if I can pull up the chat. Does that kind of answer the question? Okay, so someone let me read through so someone says, can we say that anything that has a name identifier is an L value, otherwise it's an R value? That's see, Peter asked this. That is an excellent question. Technically, it goes a little bit deeper than that. So if you want to, and I encourage you, if you want to go down this rabbit hole of what the compiler is actually doing, technically there's four different types of values. So technically, like the distinction between L value and R value is kind of like a rule of thumb way of looking at it. So I do encourage you to actually do a little bit more digging. But yes, as a rule of thumb, if it's something that is assignable, it is an L value. If it's something that exists only in the scope of an expression, then it is an R value. So generally, that would be correct. Okay, next comment is, so you can't, so John says, so you can't use a move semantic for an L value since it has a place in memory. Uh, if I'm interpreting this question, I believe what you're saying, John, is that if you've got, for instance, a constructor that requires an L value, or if you're trying to construct something with an L value, that will never be calling this R value constructor. That is correct, if I'm interpreting that right. Let's see. So Ryan says, and I hope I'm pronouncing that, man. I'm sorry if I'm not. See, if you're doing move, the memory addresses are different, but copy gives us each dog the same int address. Kind of, kind of. So with primitive types, it's kind of hard to see what's actually going on, what's actually going on under the hood. But an example that I really like that kind of just makes sense to me is imagine you've got a friend who has a house, right? And that house has got an address, and it's sitting there. Imagine you are jealous of your friend and you want a house exactly like his. You have two options. You either buy a piece of property with a different address and build a house that is identical to your friend's house, and now you have an identical house and you're no longer jealous of your friend, right? So your friend has an address with a house on that address, and you have an address with a house on that address, and they're exactly the same. That would be like copy semantics, right? And the way you can think of move semantics is thinking about your other option, right? So your friend has this house at this address, and you're jealous of your friend, and you want a house exactly like his house. You can just take his house, right? You can just barge in, this is my house now, this is my address, and kick your friend to the curb, and now he has no house. So that's move semantics, right? So in the example, you and your friend are pointers, right? So if you have move semantics, essentially what you're saying is me as a pointer is going to gain access to, I'm going to point to a place in memory, and then the old pointer is going to be assigned to null. So the actual data doesn't move, which is maybe a little confusing given that it's called move semantics. But what I want you to think about is imagine we have like some crazy um like massive expensive data type, like we've got a vector with 1 billion entries, and we just want to change which pointer has access to it. Well, rather than copying that, massive data structure into a different pointer and then deleting the first one, it would be much more efficient to keep those billion data points exactly where they are in memory and then just change what has access to it. So I hope that answers the question. Let's see. Peter asks, so does semantic refer to which constructor we use? Semantic refers to the syntax that we use to call one or the other. And so I actually, if it helps, Peter, I've got a separate example here that I think I can go over next, and maybe this will answer some more questions. And so Ryan says that helps. Okay, wonderful. All right, so next example code that we've got here, some basic includes, namespace std, nothing too crazy. And then we've got some void functions that all accomplish the same thing relatively. They just print something out. And then we've got our main function here, and we've got a vector, and we pass that vector four different ways to four different functions, and then we return from there. So if it wasn't clear before, this is the vector class. Hopefully you'll be getting comfortable with this over the next few weeks or so as you do the vector assignment. But essentially what's happening here is we're saying vector, and then we pass in as a parameter the template that we want this vector to contain. So in this case, It's going to be a vector of int type. And then we construct this vector using the multiple parameter constructor. So essentially what this will do is this one line will create a vector of int type with 10 elements, and each element will be equal to 42. So don't worry about what this is. Just think like vector, my vector is just some variable in memory. And then let's look at our four different functions. So Peter's question was, does semantic refer to which constructor we use? I would say semantic refers to the syntax that we use when we're describing what is happening in the code, right? So if we pass in a vector with nothing fancy, right? So we just say like vector int, this is our data type as a parameter. We say that the semantic is the copy semantic, right? Because what happens in this instance is when we pass the vector into this function, really what happens is, so we've got the vector somewhere in memory, and then when we call this function, that vector will be copied so that an identical copy can be then used in the scope of this new function and not at all modify the original vector that we passed in as an argument, right? So if we've got a vector with 1,000,000 elements, so imagine this has 1,000,000 elements, and then we pass it into this function, we have to copy 1,000,000 elements. So now in memory, we've got 1,000,000 elements in the first vector, and then 1,000,000 elements in the second vector, and we pass that copy to this function, and this is known as pass by value or pass by copy semantics. And so if we call pass by value, then all we need to do is pass the value that's going to be copied. And this is automatic. This is implicit. This is default. So the compiler, when it sees you pass my vector into this function, it does the copying under the hood. You don't have to worry about it. The next semantic that we're looking at is pass by pointer. And so this is, I'm going to make a note that this is a very common source of confusion that I've seen before. And I know personally, I did not understand this for a very long time. But technically, these two different semantics accomplish almost exactly the same thing. So if we pass in vector as a pointer, so we've got a vector pointer in this instance, or a reference to a vector, they essentially do kind of exactly the same thing. So what do I mean by that? If we pass by pointer, so if we pass our vector to this function by pointer, then we have the address in memory of our initial parameter, right? So in this instance, pass by pointer, if we pass in the address of my vector, that will call this function, pass by pointer, and we will have the address in memory of the original object. So that means we can modify the original object within this function, and then after this function goes out of scope, the original object is still different. So if our vector is a list of 10 elements that are all 42, and we pass that vector by pointer to this function, we can change those values for real, and they'll be changed in the rest of the code. Same thing would happen if we did pass by reference, except the only difference is that instead of passing the address of the element, we pass an alias to the element or a reference to the element. So these two will accomplish exactly the same thing. The only difference is that it's possible to pass a null pointer in this instance. So passing by pointer is a little bit more error prone because pointers could technically point to invalid or null memory, whereas a reference is expected to be something that actually exists, so it's a little bit safer. That's the only difference between these two. And then finally, we have a pass by R value, which again, the semantic here is double ampersand, and in which case we're expecting an R value to be passed here. So hence std move, which converts our L value into an R value, and therefore makes this a valid expression. And so if we go ahead, if we go ahead and compile this code, let's see, and then this was past the P. Let's go ahead and run the executable. As you can see, pretty much in order, pass by value, pointer reference R value, value pointer reference R value, calls these different things, and it works fine. So hopefully that answers the semantic question. One thing that you should just again, there's going to be a few of these, but one thing that you should just totally memorize and commit to memory for forever is the fact that these two ampersands right here means R value. And that means move semantics, always. So whenever you see the two ampersands, like in a constructor and a function, you should always know that what you're looking at is move semantics. Whereas if you see the one reference, then that's expecting a L value, or if you see nothing at all, it's expecting a copy semantics. Okay, so let's see. Hope um hope that answers that question. Let's see. Next, we've got Bao Nguyen. Now Bao Nguyen. I'm so bad with names, y'all. I'm so sorry. Will there be a recording of this for later? Yes, there will. I will post this link on YouTube. Um, and you'll be able to watch any of these parts if I maybe went over something a little bit too fast. Okay, so Peter says, I was wondering, when would we ever want to use semantics outside of the move constructor? That helps, thank you. Um, well, that's a good question, when you would ever want to move something outside of the use of a constructor. It depends on what your values are. Right? So it depends on the scope. I've got an example here, rule of five. Let's see, where is it? Um, okay, well, before we start looking at code, just off the dome, imagine we have an object that we construct purely for the sake of assignment, right? So imagine we've got like, for instance, we do some kind of calculation for a scientific equation, right? So we've got an integer that represents, some, or, maybe not an integer, maybe an object that represents some crazy host of numbers that we did all of these calculations to find. Well, after we've done all of these calculations to find this number, imagine we want to insert it into a table of data that we have that is existing. Well, although we have declared this, crazy complex data object to be an assignable L value, really all we care about is storing it in this, let's say a vector of other data points that we have. And in this instance, it would be appropriate to move our crazy complex object into the place where it's being stored in the array and have no concern for the scope in which we did the calculations, which I don't know that that's the perfect answer, but when you do start doing the vector assignment, um there will be the insert function that forces you to use move uh for the sake of efficiency, or um I think another example that might be a little bit more down to earth is, imagine you have an array and you need to expand the capacity, right? So outside of a constructor, imagine you've got like, in our example, we've got an array of data objects, and then the array runs out of memory, right? So in C++, you can't just dynamically allocate memory once you've blocked it off. It's got to be, an array has got to be contiguous memory. So if your array fills up with data and suddenly you need more space in this array, well, then you need to grow the size of the array by moving the values from the old array to the new array, right? Like that's an instance where we don't really care about the ownership or the integrity of the original array, because that one is being moved, so to speak, into the new one, and we don't care about what happens to the old pointer, if that makes sense, kind of. Uh, but if you want to look at an actual code example, I do have uh, I do have an example right here. So sometimes you might like I encourage y'all to look through like the actual built-in C++ functions, because some of them are pretty robust. Like you might be just, swapping values with another existing object, right? So in vector, there's going to be kind of an expectation of what you do, but really you can do anything inside a move constructor. So this is kind of a bad answer to your question, but what happens inside of a move constructor is kind of up to you, right? You kind of can make the rules yourself. Um, okay. So the point that I wanted to make here is that, really anything could happen inside these constructors, but the most important thing, by the way, the class is named box. It's got a private member X and a private member Y. Um, I just wanted to show you examples of what uh, each of these constructors would look like when it actually gets called in code as a reference, right? So if we see something like this, so we've got the data type on the left hand, and we've got the namespace, the value, the variable on the right hand, and we construct it in this way with, see, there's no parentheses here, note, right? No parameters either. This will cause the compiler to find the default constructor, which in this case is here, and these arguments will be passed, and it will print you called constructor. If we pass in an existing object to an object that is being constructed, this calls the copy constructor, right? So box one already exists, and it's passed as a parameter to the constructor for box two. Well, this will call our copy constructor, right? Because we need to construct box two, it doesn't exist yet, and we're constructing it based on the existing box one. If we instead move box one into box three, right? So we're turning this into an R value, and this will call our move constructor. And so depending on which one gets passed, right? Because the constructor is an overloaded function, right? So if we pass in an L value, the compiler will assign this to the copy constructor. If we pass in an R value, the compiler will assign this to the move constructor. The only difference between the constructors and the operators, or copy constructor versus copy assignment, is whether or not the thing that is receiving the new data is pre-existing or not, right? So whereas in this example, box two did not exist yet, and it gets constructed around box one. If box four, if in this case, box four was already existing, and then we assigned it to a different existing object, this is going to call assignment rather than construction, right? Because box four already exists, and then it is being reassigned, right? So when it says copy assignment operator, it's really like reassignment operator. And then same thing with move. So if we've got an existing object and we move something into an existing object, this will call move assignment. And let me go ahead, compile this as rule 5. Run this executable. And as you can see, in order, we call the constructor and then we print its value. So that's this. And then we call the copy constructor, which is this. And then we call the move constructor. And then for this particular instance, we're going to first call the default constructor, which will be this. And then we're going to call the copy constructor. I'm in the copy assignment, and then we're going to print the value. And then in this one, we're going to first call the regular constructor, and then this will call move assignment, and then that'll print the value. And then I think we had 5 values, so once they go out of scope, they'll all call the destructor. And that's kind of where you would see move probably most commonly passing to constructors. But you know, there are some edge cases in which it makes sense elsewhere in code. And then I guess the last thing, if there's no more questions that I wanted to talk about, is templates. So as you can see, I've got this class right here called foo, and this type name is going to allow us to pass in some kind of variable right here. So right now, the template for this class, I call the variable for the data type anything, just to prove that, you know, this could be, you know, fungus, right, as our variable that represents our data type. Really, it's up to you what you want this to be. See, right. And looks like we have 2 private members, and we've got a function to print those private members. And we can print the size of the object to see how changing the templated type actually changes things. So let's see, we got clear this, and this was called template.cp. Go ahead and compile. Okay, so looks like we printed out bar, the size of bar, and then the size of the object in total, right? And when passing in an integer takes 4 bytes, so therefore, you know, the size of one of the private members is 4 bytes, and then the size of the entire object itself is 8 bytes because it has 2 of these. And if we were to change this, so say it's double, right? And then we run this again. See, now it's different because the double is 8 bytes, so it prints out the size of one of the private members being 8 bytes, and then the size of the object itself is 16 bytes, right? So that's just an example, right? Imagine we wanted to have a class that takes in a data type as a parameter. Well, in this case, that's what that looks like. So that's pretty much all I had planned for today. Does anybody have any extra questions? Y'all have been wonderful so far. Very, very excellent, well formulated questions. Uh, Happy to talk about anything. We still have 10 minutes if anyone is curious about anything in particular. Let's see. So, Peter says, so when do we use templates? Oh, wait, no. So when we use templates, we need to make the function class adapt to each data type that is intended to be passed in. Yes, yes. So when you're using templates, you're going to have to be careful about what you're doing with your data type, right? So for instance, if you've got like a template that accepts, integers and you're doing, these integers multiplied by each other, for instance, right? Like assume, then if you passed a string to that same function templated, that might give you an issue because you can't multiply strings. So yes, astute question. You will have to be very cognizant about when you're using templated functions and such that you don't mess things up. Let's see. So Kate asks, where can we find the slides after the session? Let me go ahead and copy this link. Now, let's see. Um, see, chat is somewhere. I'm so sorry. See to everyone. Can someone tell me if that works? I think the slide should be posted. Okay. So let's see. Next question is Paul asks, could you drop the YouTube channel that you will upload this to? Yes, I will make an announcement on the Canvas page. That is where to look. I will do that shortly after this video is, I mean, not this video, this Sunday review is over. Let's see. John asks, can you run through the code behind the rule of 5? Yes, I'd be happy to. Okay, so in our rule of 5 example that we have here, um, essentially, the point that I'm trying to make is that the different syntax or the different semantics for constructing an object, the compiler is going to interpret those and then match you to a different corresponding function that deals with the actual constructor itself, right? So I also wanted to make it clear that when you have an object that you're defining yourself, right? So a user-defined object, then what actually happens inside of these rule of 5 is completely up to you. It's completely no man's land, right? So when maybe you want the default constructor to set the values default to 0, or maybe you have something in mind that you want to set them to. In this case, it's 42 and 93, right? Again, with the destructor, there might be something in here that you have to handle, right? So if we had like, if we had something in here like, I don't know, say a double pointer, right? So we've got some kind of dynamic memory that's going on, and imagine when we call the constructor, so it's a new, and we want to say now we've got this dynamically allocated memory. Well, because the context is different, now we've got to handle that, right? So basically, depending on the use case or the exact example that we're looking at, you might have to do different things in the destructor. This is going to come up for the vector assignment. You're going to have to think about like, okay, what should the vector look like under these certain circumstances? For the copy constructor, usually it's commonplace that you'll see a const reference to another existing object, which makes sense because we don't want to modify the other object that we're copying based on. We just want to identical copy and do no damage to the original object, which in this case, we just are assigning the private members one to one. With the move constructor, again, I was not completely faithful here. I guess I could have probably swapped both of them. So, right, and then other dot y, right? So we're just saying like, actually, yeah, maybe swap is not the right thing to do here. Maybe we want to move these. So maybe we want to say x is equal to std move other dot x, right? And so, depending on what your use is, this move constructor is actually going to look different. I will warn you that for the vector assignment, the move constructor is a little bit non-intuitive, just a little bit, because you have a pointer to an array. So rather than doing something like this, where we actually std move the contents from one to the other, all we do is we swap ownership, right? So in this case, we've got this double pointer that points to some dynamic memory. So maybe what we want to do for the move constructor is say pointer is equal to other dot pointer, and then let's see, other dot pointer is equal to, right? Maybe we want to do something like this, right? So again, the vector assignment is not going to be exactly like this. It's not going to be 100% like this, but this is that's a hint right there. And then it should be pretty much the same thing for assignment as it is for construction. The only difference is that, as you can see for the constructor types, we don't actually have a return type. So when we're specifying constructors, all we do is we specify the data type, which in this case is the box class, and then the parameter that we want the constructor to take. When we are specifying the assignment operators, technically what we're doing is we're overloading an operator. So you see this operator keyword, and this is not a constructor, mind you. The constructors look like this. So in name of object and parameters, and then the assignments look like an overload to an existing operator. So when you see this equals operator, right? So which in this case is here, this is the operator that's getting overloaded. So the compiler is overloading that operator, and that operator will be passed this parameter, which is, this is the right-hand side of the assignment, right? So and maybe a good note from earlier is that it's possible that an L value would appear on the right-hand side of an assignment, which is actually what's happening here. So box 2 is an L value, right? Because it's something that is addressable memory, right? And that appears on the right hand of this assignment to another L value, which is box 4. And so that will be caught by this assignment right here, right? So the right hand L value will be passed in here. And then some tricks that you need to do for a copy assignment is when you have copy assignment, you need to handle the edge case in which you're assigning something to itself, which is potentially a very bad error. So you make sure that you don't mess things up by this little trick right here. So if this does not equal ampersand other, then you return star this. And again, a difference between the constructor and the assignment is that you can see you've got a return type here. So whereas for the constructor, there's no return keyword, as you notice. There is, in fact, a return keyword for assignment, both copy and move. This right here is a keyword in C++ that refers to the address of the object in the current scope, right? So we're within the scope of, I guess we've got the box class in this instance. So this will be a pointer to the current box, if that makes any sense whatsoever. So this will be the address of the current box that we're looking with. And we're comparing that to the address. This is the ampersand on, not on the data type, but on the actual variable, gets you the address. And if the two addresses are different, then and only then do we actually do things. And then we want to, the data type that it's asking for is a reference to a box object. So we dereference the pointer to this object and return that. So hopefully that clears some things up. Let's see. See, Ryan says, got it. Okay, slide works. Thank you. And then let's see. We have a question. Bao Wen says, when do we use delete versus delete bracket? We use delete with no brackets when we have a pointer to the heap that does not point to an array. So in this case, we have double pointer, and you can pretty much match these things up one to one, right? So if we, for instance, say pointer is going to point to a new double, and we want to actually initialize this value, right? So in this instance, pointer is going to point to one singular value, right? So there's one double value that we're pointing to with this pointer. To delete the memory that we have on the heap, we want to do it like this, right? So if there's no square brackets in the assignment, there are no square brackets in the delete. But now let's say instead of storing one double, we want to store, I don't know, 93 doubles, right? We want to make some space. Well, because, let's see, I think that's right. Yeah. Because we called the square brackets there, we need to call the square brackets on delete. And essentially the difference between the two of them, what the compiler sees, so like this is probably too much information, but under the hood, what's actually happening is if we were to call, so pointer is going to point to an array with 93 elements, right? If we call delete without the brackets, what this does is it goes to pointer, right? So that'll be pointer is the first address in the array, and it will deallocate that one element in the heap, which will leave us with 92 elements on the heap that didn't get deallocated, right? Which is the same reason for why if we don't, like if this isn't an array, if it's just one value, it'll just delete that first value, right? But if we do have an array, then somehow the compiler needs to know that when this goes out of scope, not only do we need to delete the first value, the brackets indicate that we need to delete every single value, and in this case, there's 93 of them. So excellent question. And okay, that's three. I'm gonna go ahead and I think that's enough for today. If anyone has any extra questions, be happy to answer, but I think y'all have probably slogged through enough. So yes, Festus, thank you. I'm gonna go ahead and